So the first presentation will given by a video presentation because it's nighttime in the US and it's very convenient to stay so long. So I hope this will work now with the video.
As a scientist at the Brookhaven National Laboratory. First, I'd like to
now we can hear him. Thanks.
And Qiang Li, Qiang Li, and a former postdoc at Toshinori in my group are involved in the single crystals and thin films growth. We have Dan Navalli and Peter Johnson involved in electron spectroscopy. Pedro Lozano and Chen Zhang are in the transport characterizations. This is the outline of my today's talk. I will start with power applications of superconductors and discuss the TC and JC enhancement in ion chalcogenide superconducting thin films. Then I will go to the quantum computing, arguing that ion chalcogenide superconductors could be a good candidate for topological qubits. Then I will discuss some of our recent work on topological states in ion chalcogenide superconductors. For more than a decade, our group has been involved in the power application of superconductors, more specifically on high temperature cuprates. And those are the projects funded by the US Department of Energy, ARPA-E or ERE. We're involved in the development of superconducting magnetic energy storage device for grid and applications to rotary machines, including the wind turbines and the next generation electric machines. In the higher temperature end, we were involved in the transmission lines. As you can see, each applications occupy a specific area of the phase diagrams, with the cements mostly applicable at a lower temperature and higher field. And for transmission lines, at a moderate field and higher temperature, rotary machines occupy the middle section of that. As we know, the TC, HC2, JC, and anisotropy are limiting factors for large-scale application of superconductors. More than a decade ago, I have shown this plot, made a comparison of these critical parameters for high TC cuprates, low TC materials, magnesium diborides, and ion-based superconductors. The potential of ion-based superconductors for large-scale applications is clearly to see for its very high upcritical field. At that time, the development of the films and tapes and wires are in an earlier stage. Now we have reports to show that ion-based superconductors can have critical current densities above 10 megaamps per centimeter squared. And this is to show the revised figures on the right-hand side. Now, our research on ion chalcogenide superconductors is funded by DOE BS. And we focus on the growth of single crystals and thin films and characterize their properties. On the single crystal side, we made a large number of ion chalcogenide superconductors and single crystals in different composition and those are supplied to many groups in the world and for the fundamental science study. On the thin film side, we're the first group to grow the ion chalcogenide superconducting epitaxial films on various substrates with a very high crystallinity and superconducting properties. We also made this film in a flexible metal substrates. At the Brookhaven, we have two thin film growth chambers. One is the older ones, is the generic pulse laser deposition systems, PLD system. Then the newer ones is a MBE-based type of chambers where you can go to UHVs, allow us to grow atomic layer by layer films of ion chalcogenides. Now, in the middle part of the image, it shows the TM cross-section of the films grow on a YSC with a cerium oxide buffer. And later we found that when we use a cerium oxide buffer, films generally have a better quality. In the early days, to our surprise, we found the films we made generally have a higher transition temperature than the bulk single crystals. Now showing this figure is the normalized resistance as function temperature. The green symbols represent the superconducting transition of the bulk single crystals at a TC around 14.8 kelvins. Now the films grow with the cerium oxide clearly has a transition temperature up to 20 Kelvin. That is more than 30% of enhancement of TC. We also found these films made with cerium oxide buffers can have a very high current density. Showing here the plot of the JC's function of the magnetic field and temperature. Routinely, we can achieve the JC about 1 megam per centimeter square in these iron chalcogenide films. And this is not only for the films grown on YSC single crystal substrate, but also on flexible metal substrates such as rabbits. And the in-field performance is very good too, and extended all the way to 30 Tesla and lower temperature of that. Now from this, we argue that iron chalcogenide superconducting films can be usable for applications such as high field magnets. To further enhance the critical current density in these iron chalcogenide films, we look for other artificial pinion centers. In this case, we use ion radiations. Now we're sending in the high energy ions, you can have several events happens in the materials. You can have these parasitic events produce heat, such as the ionizations, or just simply rattle the lattice, produce phonons. Those are the minor events of that. What we want is a recoil event. This is the collision between nuclei and ions. And this is the events that will be useful to produce the pinion centers here. Now for the films we have, it's very thin. So to increase the efficiency, we put a aluminum foils on top of that. And this is the simulated result showing on the left-hand side. We put a 1.5 micrometer thick aluminum foils on top of 120 nanometer thick iron chalcogenide films. Then we can make this recoil events happen, or we call it brackets, right inside the films of that. And this increases the efficiency of the ion radiations. Now the TEM images showing in this slide are the microstructure of the irradiated films with different energies of ions. For instance, you send in the low energy protons and you produce defects, which is like small zippers, which is locally disturbed lattice of that. But if you're sending a high energy gold ions for 6 MeV, you produce a large cluster of defects shown on the right hand of the figures of there. Now, if you have the low energy protons, you will need to have a higher dosage. For instance, in this one, to show the effect, we go all the way to 10 to the 15th protons per centimeter square. For the high energy gold ions, you don't need that much dosage of that because the defects is already big. You put that much of 10 to the 15th, you basically cover the whole thing. So in this sense, we will only need to have a 10 to the 12th ions per centimeter square would be sufficient to put enough defects in the films. So here we show you the result of irradiation on the TC of the iron chalcogenide films. For the low energy proton irradiations, we generally found that TC can be enhanced. For instance, the before radiations, we have TCs about 18.5 Kelvin middle point, but if you're after radiations, we can get the zero field TC close to 19 Kelvin. But for high energy gold ion radiations, the TC very little change was observed. For instance, it shows the insert of this on the right hand of the figure of that. But overall, we see a slight enhancement of increase of the normal state resistivity. Suppression TC is really minimal. Now, to understand the origin of the TC enhancement in this low energy proton irradiated films, we performed a detailed TEM structure analysis with the strain mapping of this low energy irradiated iron chalcogenide films. A is a high resolution TEM image. The insert 1 and 2 are the diffractogram from the circled areas 1 and 2, respectively, one with defect, one without defect. The strain mappings are shown in the figures from C and D. Now, if it's a blue, it's a compressive strain, and yellow is a tensile strain. As you can see that in very nanoscales, you have this compressive strain, which we know to enhance the TC. So we believe that this created cascade defects with this nanoscaled compressive strain, and proximity effect gave the overall the TC enhancement in these films. Now we found that this low energy proton irradiations not only enhance the TC, but also enhance the JC of the films. Showing the left-hand side is a figure of JC plotted as a function of temperature field at 4.2 Kelvin. Through the radiations, JC is doubled. Now, this JC enhancement was also observed in all fields and directions. And this is showing in the figure in the middle of this slide. And the JC is plotted as function of the angles, and the data were taken at 4.2 Kelvin in the magnetic field as high as 25 Tesla up there. Solid symbols are the irradiated ones, and open symbols are non-irradiated. As you can see that overall JC is enhancement in all directions and fields. Now, this enhancement was also observed in 6 MeV gold ion radiations at 10 to the 12th ions per centimeter square dosage there. This is represented in the figure showing on the right-hand side, taking at 4.2 Kelvin. It's also amazing to know that this ionic liquid gatings can enhance the TC of ion chalcogenic films dramatically. Now, showing in this one is an example done by my student, former student Chen. He put the ionic liquid on top of this ion chalcogenic films and applied the gating voltage of that. As you can see that TC up to more than 30 kelvins was achieved in gated films. Now, if you release the gate and TC back down and recover the original behavior there, this kind of reversible and doubling the TC could be very interesting in the future studies. Now I'm going to switch gear to talk about the potential of ion chalcogenic superconductors for quantum information systems. Now let me start with this cartoon picture, which you may have seen different versions, showing Alice is communicating with Bob in a quantum space enabled by a bunch of quantum hardware, quantum computers, quantum networks, and quantum transducers. An ideal quantum transducer will be able to seamlessly pass information between different modalities. For example, a quantum computer operating at a gigahertz and a quantum network operating at optical frequencies. At the heart of the quantum hardware is the quantum materials. There are many types of quantum materials, conventional or emergent. Here, let's narrow down a little bit to those essentials for quantum computing hardware. There's a good review article published recently in Science magazine by Natalie de Leon from Princeton. There are about 5 quantum computing hardware platforms leading the way: superconducting circuits, quantum dots, Carter centers, trapped ions, and topological protected systems. Each has its own opportunities and challenges. Superconducting circuits have made it to market. You can buy a quantum computer based on superconducting qubits. The rest are in various stages of development. Now, in the following, I will discuss quantum materials enabling topological protective systems. Now, let's look at some possibilities for next generation qubits in the areas of superconducting and topological systems. Majorana and the chiral qubits are examples of topological qubits. Many of you might aware of the Majorana qubits. I bet most of you are not aware of the chiral qubits. The chiral qubits uses chirality in topological materials to create base states, while terahertz wave will be used for controlling, much the same way as you use microwave to control the superconducting qubits. Now, for superconducting and topological qubits, we're dealing with 2 most famous quantum materials, superconductors and topological materials. The distinction between these 2 types of qubits and others like trapped ions is that here the operation is based on macroscopic quantum phenomena. Such a macroscopic quantum phenomenon involves millions of electrons and is dictated by the entire electronic structure of the system, not just a single spin or a single atom. When we talk about Majorana qubits and topological quantum computer, we should mention the work of Kitaev on the fault-tolerant quantum computation by anyons. Now, this is from the basis of this topological quantum computing using non-abelian anyons. And these anyons can be realized in the fractional quantum Hall states, Majorana zero modes in topological superconductors and superfluids, or the quantum spin liquids. Now let's look at the Majorana qubits, which is based on a theory that trajectories of Majorana quasiparticles can be arranged to be topologically distinct that forms the base states for the qubits. For such topological qubits, the advantage here is that error correction may not need it. That has been the critical issues for superconducting qubits or other 2-level energy states. Now, in order to make a Majorana cubics, you have to first have the Majorana zero mode and also know how to do the braiding. Now, actually, right now, we don't have any of them. So the research here is that first to find out, identify what is a reliable Majorana zero mode. The earlier and the most notable proposals to capture this Majorana zero mode is in the hybrid systems made of superconductors and the semiconductors with a strong spin orbital coupling. Now, because we know that the quasi-particle excitations in superconductor has this particle-hole symmetry, the quasi-particle excitation in superconductor should occur in pairs at the energies plus minus E. So this gave rise to zero energy excitation or zero energy mode. So the bound states had the zero energy. Now, because we know this Majorana zero mode are likely to bound to the topological defects. So a likely place proposed to capture this Majorana fermion is at ends of the semiconductor nanowire with a strong spin orbital coupling and in proximity with the conventional superconductors. The evidence of Majorana zero mode has also been reported in multiple publications involving ion Qiang superconductors using the same single crystals grown in our group. Now, the Majorana zero mode are proposed to be present at the end of this magnetic vortices. A manifestation is a sharp zero bias conduction peak within the vortices. But why we have to use ion Qiang? That's because they have all three ingredients necessary to produce Majorana zero mode. Of course, the debate is still going on in the interpretation of the data, which I will not get into. Now let's look at the requirement for observing the Majorana zero mode in topological superconductors. You need to meet three requirements. You have to have a strong Zeeman splitting. Of course, then you need a magnetic field presence. And you need to have a strong spin orbital coupling and the proximity induced superconductor gap. This Zeeman energy has to be bigger than the combination of the superconductor gap and the chemical potential. So in this sense, the ion Qiang superconductor fits the bill. Now you have tellurines, which is heavy metal, produce a strong spin orbital coupling. You have superconductor produce the gap. And also possibly you have some of the ion impurities produce the intrinsic magnetic field there. Now the trick here is that you have to reduce the superconductor gap and also to have very small chemical potential so that Zeeman energy will be bigger than the combination of the both. And this is the research where you really have to go in for. And the figures showing here are the result of electronic structures of optimum doped ion tellurine selenium at 0.55 and 0.45 respectively, using angular resolved photo emission spectroscopy, ARPAS. Figure A to D show the spectral intensity measured in the vicinity of the gamma point as function of temperature, 20, 14, 12, and 10 Kelvin, respectively. Superimposed over the measured intensity, the white dot curves show the peak intensity and red dashed curve shows the underlying the cone. Now, there are several interesting features that I want to point out here. First, you see these direct dispersions that represent topologic nature of the systems with a very low chemical potential, and this is good to see the Majorana zero mode. And also the development of a large temperature-dependent gap at the direct point and associated mass acquisition is an indicator of some form of trireversal symmetry breaking associated with the bulk superconducting transition. And this signals they could have some surface magnetism and possibly coming from the interstitial ions. The spectrum here are taken along the normal direction in ion tellurine selenium. Two samples, A has lower tellurine concentrations and B has a higher tellurine concentration. At 20 Kelvin, the increased tellurine's concentration are moving from the 0.055 to 0.7, result in an increase in the intensity of the peak. And then vicinity of the direct one clearly shown the data is related to the tellurine concentration. And it's increased the state signal that stronger spin orbital coupling is realized in the sample B. Although we are a bit far away from to build a practical systems using ion Charcogenic superconductors for energy, high field, and quantum information science applications, I think the potential is there, and it's interesting to pursue the potential and also for fundamental studies. So now let me summarize my today's talk. I have shown that low energy proton radiations can produce cascade defects in the ion Charcogenic films, leading to enhanced TC from the nanoscale compressor strain and proximity effect, as well as a strong pinning centers to enhance the critical current density. I also show you that the evidence of time reversal, symmetry breaking, and social mass acquisition in the topological surface state, the superconducting transition in iron, tellurium, and selenium. Now, here's a short advertisement for postdoc positions in my group at Stony Brook University. And if you are interested, please contact me.
Okay, Kazu, thank you for playing the video, and thank you for Qi, of course, to record this. Kazu, so